two sets of suggested problems. So one of the suggested problems will appear just as it is on the website. Another problem will be kind of the ones on the suggested problems, and third problem will be different. Okay, so let me recall that last time we discussed we started the last lecture by discussing the following thing. Suppose that there is unique factorization of Gaussian integers. Suppose the Gaussian integers do admit unique factorization of the prime numbers, the Gaussian prime numbers. Then we use this, we actually use this to show that we can, from this we can derive the parameterization called Pythagorean triples. And then we try to do this, the same thing in another kind of integers together with symbols square root of -5, and somehow we failed, and we understood that the reason why we failed was because there wasn't any kind of unique factorization in this kind of integers. So once again, let me just recall what was the end of last lecture. In this kind of integers, let me once again recall what these integers are. A plus square root of -5b, segment A and B. So in this kind of integers, you can multiply numbers, you can add them, you can subtract them. So you have all the usual arithmetic operations. You can factor integers as a product of things which should not be factored any further. But in this kind of integers, we have such an identity. 3 squared is equal to 2 plus square root -5 times 2 minus square root -5. So 4 minus 5 is equal to, is 2 squared. Wait. Yes. So yes. 9 is 3 squared. 3 squared minus 5.
4.
Okay.
3 squared. 3 squared. 2 plus. 2.
So it's 4.
We get minus
4 plus, okay, yes, sorry. 4 plus 5 is equal to 9. Yes. Thank you. Okay, so in this kind of integers, we have this kind of factorization, and moreover, 3, this number, 2 plus square root -5, and also 2 minus square root -5 can't be factored. I mean, it can't be factored in any non-trivial way. Of course, it can be factored, say, 3 is minus 1 times -3, or 1 times 3, but not in any non-trivial way. Not in a way which doesn't involve plus or minus 1. So, in this kind of integers, we have a funny thing. We have what should be prime numbers, numbers which cannot be factored as a product of something else, and we have such an identity. One prime number squared is equal to a product of 2 other prime numbers. And these are all distinct primes. Of course, in usual integers, there is nothing like this. If you have some number, it can be factored into prime factors in a unique way. Well, not exactly unique, you can reorder stuff, you can maybe multiply things by -1s, but essentially in a unique way. In this kind of integers, no, nothing like this. Here's an example of factorization of the same number, same answer once you multiply all these things, but different factorizations. One of them is just one prime number squared, another one is a product of 2 different primes. So we see that they are really distinct. So the conclusion is, well, first of all, it is useful to have the notion of unique factorization to be able to take something and factor it into a product of prime numbers, because we've seen, for example, it gives us parameterization of Pythagorean triples. It's kind of useful. And well, another thing, it's not automatic. It's really not that automatic that in this kind of integers, or well, in this kind of integers, Gaussian integers, We do have any factorizations. Well, in fact, here we don't. So what is the reason why here we do have a factorization? So today I'm going to discuss this question. So maybe before I go on, any questions? So maybe you want some other reminders about what's going on, or any questions about Gaussian integers?
Yeah, you get unique factorizations, so there's only one way to factor any given formula or set.
Yes. So the idea is that you start with from a number here, you write it as a product of things which are not factorable so any further, and the claim is in these kind of integers you can do it in only one way. Well, essentially in only one way. You can of course reorder the prime factors, you can multiply each factor by plus minus 1, plus minus I. Well, I mean, for example, if you have something like this, T1 times T2, you can write this in this way, I times T1 times minus I times T2. So this iteration of these prime things are actually different primes, but well, they are different after multiplication by u. So there is small ambiguity, but essentially there is only one way to factor. Other questions? Okay, so I will try to do it like this. I will try to formulate notions that we are used to from usual natural numbers or integers, and to formulate precisely what they mean in these kind of integers, and then repeat all the arguments which I hope will be equally applicable to the usual integers and to this kind of integers. So maybe first notion, like the very first notion is divisibility. What does it mean that one number divides another number? So we have some definitions. Let's say that A is a divisor of B if B is some quotient times A. Here A and B and quotient are required to be Gaussian integers. So that's just the definition. One number is said to divide another one if the other one is the product of this number and something else. Another thing, well, kind of theorem. I mean, it's a fancy word, theorem. It's almost obvious, but still, in usual integers, we have the property. If some number, if A divides B and B divides A, then, well, if A divides B and B divides A, then, so what happens in usual integers in this situation?
They're equal.
They're equal, well, almost. Up to a sign, yes. So in this situation, say 5 divides minus 5 and minus 5 divides 5. They are not equal, they are equal after a sign. So in usual integers, I would write A is equal to plus minus B. In this kind of integers, I would say that A is U times B and U is a unit. So they are almost the same, it's just the quotient is a unit. And the unit, if you recall, is, well, I can say it like this, it's either plus minus 1 or plus minus I. Another thing is, another characterization is the Gaussian integer whose norm is equal to 1. Or yet another characterization is a Gaussian integer such that 1 over this number is also a Gaussian integer. So let's see what we have here. The proof is, well, of course it should be very easy. If A is A divides B and B divides A, then A is some number times B, B is some number times A. So you can write actually so then A is equal to Q1 times Q2 times A. Well, I want to write it 1 is equal to product of Q1 and Q2. I can't really do this because, well, nobody guarantees me that A is, well, that A is not equal to 0, so I'll have to consider two cases. If A is equal to 0, then the theorem is correct. Because in this case, well, actually, well, if A is equal to 0, yes, if A is equal to 0, then B is also 0. B is equal to 2 times A is also 0, and then 0 is equal to 0. So A is equal to B. So it's kind of correct, but in a trivial sense. But if A is not equal to 0, then 1 is equal to Q1 times Q2. These are Gaussian integers whose product is equal to 1. So Q1 is a Gaussian integer, such that 1 over this number is also a Gaussian integer. It means it is a unit. So Q1 is a unit, hence A is a unit times B. So once A unit means 1I minus 1 minus 1. So this kind of statement, well, holds, but just like it holds in usual integers, except that what do we mean by a unit? Well, in both cases we mean just such a number, such that 1 over this number is also an integer, but in this case, well, in the usual integers it's plus or minus 1. In this case, you have two extra units. It's plus minus 1 and plus minus I. So, well, we proved a very simple property of divisibility. You can check some other properties of divisibility, which you are used to. Say A is a divisor of B, and B is a divisor of C, then A is a divisor of C. There are many such properties. You can check all of them. Well, it's really obvious. What's not that obvious is the fact that even in these integers, in Gaussian integers, you can divide with remainder. Before we do this, we should explain what we mean by division with remainder. So division with remainder given in the Gaussian integers, which is not equal to 0. We can do the following. We can write A in the following form. Some quotient times B plus some remainder. Now the question is, what do we mean by remainder? In usual integers, we mean just some number between 0 and B. So it's some number which is smaller than the thing by which we are trying to divide. In Gaussian integers, you can't really compare two numbers. You can't say what is bigger, 2 plus 3i or 4 plus 1. Which one is bigger? Well, the question doesn't really make sense, but we can compare the norms. How long is the vector from 0 to this number? So we can write A in this form with remainder whose norm is smaller than the norm of B. It's a positive integer. Norm of any number is a positive integer. We can compare it to positive integers. Oh, sorry, non-negative integer. We can compare them. Which one is larger? And the claim is, well, we can always make a division with remainder. try to do an example and then we'll try to prove the general theory. Say I want to divide, example, let me try to divide, say, 2 plus 3i by 1 plus I. So what I'm trying to do, I'm trying to write A as a product of the quotient times B. Or maybe let me change it like this. Quotient times B plus some remainder, and the norm of remainder smaller than norm of B, which is 2. So how can I accomplish this? Yes. Okay, and then 3i, what is the norm of 3i? It's 9. So it's too large, right? So the suggestion was, A is 2 times, so this is 2 plus 5i is 2 plus 2 times 1 plus I plus 3i, but the problem is this is not the remainder, it's too large. Normal 3i is 9, oh it's not good, so it doesn't work. Well, the problem was, of course, we tried a wrong quotient. This number is too far from the actual quotient. So what can we do? Well, I'm not saying that I'm not claiming to do this.
Okay, we just want one possibility.
Yes. So like in usual numbers, you can say well, 5 is 2 times 2 plus 1, or 5 is 3 times 2 minus 1. The quotient is well, either 2 or 3. It is close to the actual quotient, 2.5. So we could round it down or round it up. Yes.
So you could just actually divide A by B.
Okay, let's try this. So in usual integers, if you want to find the quotient and the remainder, you can do the following. You can take A actually divided by B, find an answer, actual answer, and then well, round it down or round it up, and see what we get. So let's try the same procedure here. Let me take A over B. B is 2 plus I divided by 1 plus I. Well, let me multiply and divide both by the conjugate expression. So in the denominator we have 1 squared plus 1 squared. In the numerator we have 2 plus 5i times 1 minus I. Now opening the brackets. 2 plus 5, 7 plus 5 minus 2, 3i. So the actual quotient is, let me write it like this, 3.5 plus 1.5i. Well, now I have several choices. I can round it up or down. Well, I can round it up here. Here, well, I have 4 choices basically. All 4 of them will be equally far from the actual quotient. So let me take some try. So we have 3 plus I. Well, let's see. What is A minus 2 times B? What is the remainder? Well, let's see. It's 2 plus 5i minus q, which is 3 plus I, times b, which was 1 plus I. Plug here in single computation, just open the brackets, and we get 2 minus 3 and minus 1. So it is 2 minus 3 plus 1, so it's 0, plus 5i minus I and minus 3i, so plus I. So we get I. So you see that we did accomplish what we tried. Norm of this remainder is indeed just 1. It's 1 squared, it's 1. Which is smaller than the norm of b, the thing by which we were trying to divide, which was 2. Well, of course, we could try other things here. I mean, this worked. Maybe some other things also could work. Maybe 4 plus I would also work. Well, let's try to put the general theorem. So, general theorem. Well, let me do the same thing. I want to divide a by b with remainder. Let me divide it exactly and then round it. So let x be a divided by b. The actual quotient. It is some complex number. It is a complex number. I'm not claiming it is an integer. Just some complex number. I don't know anything about it. But I do know that there is an integer, Gaussian integer, which is close to it. So let q be Gaussian integer changing notation. I have to say this is Z and this is Q. Oh, this is Q. So let Q be Gaussian integer which is close to this number Z. So if Q is Q1 plus I times Q2, I want and so decide that P is this and Z is X plus Y, then Q1 minus X is at most 1/2 and Q2 minus Y is at most 1/2. So I can take the coordinate, the x coordinate and the y coordinate and run and take an integer which is close to it. I can always find an integer which approximates a given number, a real number, up to 0.5. In other words, well, maybe I'll try a picture. So if you draw the complex numbers on the plane with x coordinate and y coordinate being the imaginary axis. So if you draw them here, you have your number q somewhere, and around it there are some Gaussian integers. So 0, 0, 1, 0, 2, 0, 3, 0, I, 2i, 1 plus I. So lots of Gaussian integers around. Let me take, well, just the point in this basis which is the closest. So I see that this point is, well, it's to the right, to the left of this middle line. So I move to the left. I see that it is, well, say, closer to this line than to this line. So I move here. So this will be my Z. Sorry, so this was Q, this was Z, and this is Q. So Q is a Gaussian integer, which is a good approximation to my actual function Z. That's what I'm saying. Okay, so we have this, and now what can we say about, well, first, when we do the following, the norm of Q minus F, the norm of difference, this difference, how far are the numbers from each other? Well, the norm is some x coordinates plus y coordinates. Each of the coordinates of the difference is at most 1/2. So this is 1/4 plus another quarter. The distance between the actual, sorry, not the distance, but the square of the distance from the actual quotient and our approximation is at most 1/2. So yes. Okay, so let me. Now I want to understand what is the norm of this remainder. The remainder being A minus the quotient times B. I want to understand what is the norm of this thing. Well, I can write what's here in the following form. B times A over B minus Q. Just very simple factorization. But our norm is norm of the product is product of the norms. We've seen this property when we discussed complex numbers. So here we have norm of B times norm of the following number. A divided by B minus this quotient. But look, this thing, A over B minus the quotient, is exactly this thing. The quotient minus the actual quotient is Z, Q is the approximation. So it's the actual quotient minus the approximation. And we decided that this is at most 1/2. So this is at most 1/2 norm of B. Well, technically this is smaller than norm of B. It's smaller even than 1/2. So it's more or less like in usual integers. Not only we can divide this remainder such that the absolute value of remainder is smaller than the thing by which we are trying to divide, but we can always make it smaller than half of the thing by which we are trying to divide. Because we can take, if we're dividing, say, 5 by 3, well, we can get a remainder of 2, but we can replace it by saying it's a remainder of -1. So by using negative numbers as well, we can do a little bit better. Same thing in complex numbers. Not only we can divide this remainder and get norm of remainders smaller than the number by which we are trying to divide, it's smaller than 1/2 of this number. So same phenomenon. So what's interesting about this thing, it looks very simple, and well, it is very simple. But what's interesting is that's the heart of what's happening. That's the reason why we have unique factorization in Gaussian integers and we don't have unique factorization in some other kind of numbers. In this kind of numbers we do have an algorithm for division with remainder. We do have division with remainder. In other kind of integers which I showed, there is nothing like this. And more generally, well, I don't have enough words to describe in what generality I can say it, but well, still, more generally, if you have some kind of number system, by which I mean, well, somewhere where you can add, subtract, multiply, and you have some kind of norm, then if there is division with remainder, then we do have unique factorization in this kind of numbers. So this part will be very general. So in a sense, this is the heart of the reason why there is unique factorization in our kind of numbers, in Gaussian integers. The rest of the arguments for why we have unique factorization will be applicable in much wider generality. So maybe any questions about division with remainder? once we have division with remainder, we can formulate what GCD is. So definition. Actually, we can always formulate what GCD is. I say that C is GCD of A and B if two properties. One property, it is the divisor of both A and B. So if you want the greatest common divisor, you want it to be an actual divisor. Another property, if D is the divisor of A and B, then C, then D divides C as well. Then D is the divisor of C as well. So this number C divides all the divisors of A and B. So among these numbers, it is the largest in the sense of division. And it is divisible by all the other divisors. Well, in our case, yes, we are talking about Gaussian integers, but once again, this definition is a little bit more general. You can talk about usual integers, you can talk about Gaussian integers, you can talk about, let's say, any ring if you know what the ring is.
Like for usual integers, if to use this definition, how do we choose positive?
Yes, so the GCD is not really, unique. It is defined after unique. You can always multiply it into usual integers by plus or minus 1, and Gaussian integers by plus minus 1 or plus minus I. So first claim GCD of A and B is defined is unique after unique. Which means if you have two different numbers which satisfy these two properties, then one of them is a unit times another. So if C and C prime both satisfy these properties, then C is a unit times C prime. So in this claim, I'm saying the GCD is defined. So sometimes in certain kind of integers, even this notion of greatest common divisor of two integers just is not defined. But every time it is actually defined, every time you can find a number with these two properties, it is essentially unique after multiplication by unit. So proof is really simple. So if both C and C prime are such things, then first of all, C divides A and B, C prime divides A and B, they are divisors. Now, well, if you have any divisor of A and B, for example, C prime, then C divides. So from this it follows that C is the divisor of C prime. And vice versa. C is the divisor of both A and B, hence this number divides C. So C prime is the divisor of C. So I'm using this property. If some number, for example C prime, is a divisor of A and B, then it is a divisor of C. So C prime is a divisor of C. Well, but now I have two numbers, one of them is divisible with the other and the other way around. We just prove that C is a unit of C prime. which is gerund square root of -5, it's always true. But the existence of GCD is not automatic. Is there some number which satisfies these two properties? Well, it's really not that automatic. So another thing, in Gaussian integers, we do have GCD. So theorem, in Gaussian integers, GCD A and B exists for all or maybe non-zero. For any non-zero Gaussian integers, we can talk about the GCD of these two Gaussian integers, and GCD of A and B is of the form number 1A plus number 2B. Sum number 1 and 2 is also so just like in usual integers, we can always write, well, we can first of all talk about what a GCD is, and we can write this number, the greatest common divisor, as a linear combination of the original numbers with integer coefficients. And this time with Gaussian integer coefficients. Well, and to be honest, the reason is, well, just the usual Euclid problem. You can divide with remainder, you can divide A by B with remainder, then you can divide B by the remainder of that, and so on and so on. The norms of remainders become smaller and smaller, eventually the remainder will have to be 0, and then we can make some back substitutions. So that's one of the ways to explain usual integers. Maybe we did this, so let me formulate a different proof, maybe not that constructed, but still a proof. So for this, let me just consider all possible such linear combinations, and among these linear combinations, choose the one which has the smallest norm. So let's see the number of the form number 1A plus number 2B with the smallest norm. Well, to be honest, that's not really what I want. Of course, I can just make this number to be equal to 0. I can always make it equal to 0, say B times A plus minus A times B. This is always equal to 0. I want the smallest non-zero number. So B, the non-zero number. Of such a form, so I change the coefficients lambda 1 and lambda 2. I get a collection of numbers. Among these numbers, I choose a number with the smallest norm. It doesn't have to be unique, just one number whose norm is the smallest. Norm is an integer. In every collection of integers, I can follow its natural number. In every collection of natural numbers, I can always find what is the smallest one. Well, now I claim that this C is in fact GCD, which means it is a divisor of both A and B, and if you have any other divisor, then this other divisor is a divisor of C. So let's verify these two properties. One property, if D is a divisor of A and B, then D is a divisor of C, just because C is of this form, lambda 1A plus lambda 2B. A is a multiple of D, B is a multiple of D, hence C is a multiple of D. That's almost obvious. The other part, the fact that D is divided, that C itself is the divisor of both A and B, well, it's less obvious. I claim that C is the divisor of B, is the divisor of A. So here's the proof. When we write A, well, when we divide A by C, this remains. So let me write A as a quotient times C plus some remainder. In this, and here I'll make sure that the norm of remainder is smaller than the norm of C. I can do this because I work in Gaussian integers. It's not automatic. Like all the previous arguments, this one is not automatic. I just, well, I had to work, I had to show that actually I can do this. Well, now I don't know, I can't do this. Well, I want to show that A is actually divisible by C, so I want to show that R is 0. But look, what is R? It's A minus the multiple of C. It is A minus some multiple times this number, lambda 1A plus lambda 2B. But then it is a linear combination of A and B with some integer called Gaussian integer coefficients. It's A times this Gaussian integer 1 minus lambda 1 cube plus minus lambda 2B. So it is a linear combination of A and B with some Gaussian integer coefficients. Lambda 2 cube. But its norm is smaller than the norm of C, because it is the remainder. By definition, well, it must be equal to 0, because C was the number of such form with smallest possible norm. If something has even smaller norm, it must be equal to 0. So since C has the smallest norm, non-zero linear combinations of A and B. Linear combinations. It's got some integer coefficients. R must be equal to 0. Once again, we have two properties. Norm of R is smaller than the norm of C, and R is a linear combination of A and B with coefficients which are Gaussian integers. The definition of what C was, well, R must be equal to 0. So hence, A is the quotient times C, hence C is the divisor of A. And of course, similar considerations apply to B. It's not different from A. They have symmetric rows. So similarly, C is the divisor of A. So once again, we take all possible numbers of the form some Gaussian integer times A plus some other Gaussian integer times B. Among all these numbers, well, there are some numbers which are equal to 0, we forget about them. Among the other ones, we find some number whose norm is the smallest. I claim that this number is the divisor of A, automatically. Why? The reason is, well, when we divide A by this number with remainder. The norm of remainder is smaller than the norm of C of this number. Well, but also the remainder is a linear combination of A and B. So it is in this kind of collection, linear combinations of A and B. But its norm is smaller, hence it is actually equal to 0. That's our. So any questions about this?
Why don't you reduce like theory, like you were mentioning, or why don't you use that?
So there is a choice to be made here. I mean, from the pedagogical point of view, I could introduce the general words like ring, a ring is using algorithm, ring is interpretation, principal ideal of ring, and so on. This is all done in course something like Gauss-Steven fields or something like this, and we will do this. Well, I'm not sure that it's strictly necessary for our purposes. So here it will be just faster to do it for Gaussian integers. If you have the idea of the ring in the background, if you do know some familiar rings other than these ones, then you will have, well, then you'll probably be able to apply the same ideas in this context. So for example, if in a line you have, I don't know, the ring of polynomials in one variable with coefficients of phi, well, you can try to see which steps do work there, which don't. But I'm not trying to teach kind of abstract thinking here. I'm trying to teach what happens in this usual kind of, almost usual kind of numbers, Gaussian kind of numbers. But if you do know the more general notions, and if you do have some trivial examples of rings, interesting examples of rings, you can take this lecture and try to see which parts of them will it work in more generalized. And so I do try to make the arguments as general as possible. Okay, so maybe we'll make 10 minutes break and then we'll continue through the factorization.